All right, let's talk about a really powerful but also kind of dangerously misunderstood tool in the Go standard library, the sync.Map. Now, it promises this amazing high-performance concurrency, but as we're about to see, if you use it in the wrong place, it can be a total disaster.
So it all starts with this paradox, this mystery that stumps developers all the time. You throw more hardware at a problem, right? You get a brand new, shiny 32-core server, and you're expecting this massive speed boost. But instead, your application just grinds to a halt. What is going on here?
And this is exactly the situation our developer, let's call him Ethan, is in. He's just staring at his performance monitor, and he's completely baffled. I mean, all that expensive hardware is just sitting there, totally idle, and he has no idea why. This is where our investigation really begins.
So let's call this first part what it is, the 32-core paradox. It's this classic scaling problem that so many engineers run into. You add more power, you get more processors, but for some reason, the performance actually gets worse. Let's break down exactly why that happens. So you pop open a CPU flame graph, that tool that shows you where your program is spending all its time, and bam, there it is, the smoking gun. A huge chunk of that time is being wasted inside a read-write mutex. This is our first big clue. The very thing that's supposed to be managing all this concurrent access is actually causing the traffic jam.
Okay, so why is the mutex the problem? Well, it turns out the mutex is just a symptom. The real issue is something much deeper, something happening at the hardware level. It's time to unmask the true villain of our story, lock contention.
Lock contention. This is what happens when all 32 of those super powerful cores try to grab the exact same lock at the exact same time. They all end up in this virtual line, fighting over one single tiny piece of memory, and the whole system just slows to a crawl. And this just perfectly illustrates the problem, right? In theory, an RW mutex is great. It lets tons of processes read data at the same time. Awesome. But in reality, when you get to this massive scale, just keeping track of who is reading means updating a counter. And now all 32 cores are fighting to increment and decrement that one little counter. They literally spend more time arguing about the lock than actually doing their work.
So, how in the world do you fix this? Well, for this very specific high-contention scenario, Go's standard library has this specialized tool designed to sidestep this exact problem. And I want to be clear, this is not a general replacement. It's a precision instrument. Enter the sync.Map. Now, what's so interesting here are the trade-offs you have to make. To get all that fancy internal concurrency handling, sync.Map makes you use methods like load and store instead of those simple brackets we're all used to. And because it was built before Go had generics, it completely gives up type safety. That means you have to manually check the type of the data you get back every single time.
But the benefits of sync.Map don't stop at just avoiding lock contention. Oh no, it has another really cool trick up its sleeve. And it helps solve a really subtle but incredibly dangerous bug that can bring entire systems down: the cache stampede. Just imagine this. Your cache is empty, and 1,000 users all request the exact same piece of data at the exact same millisecond. They all see the cache is empty, so all 1,000 of them just hammer your database at once. That is a cache stampede. And believe me, it can take your entire system offline.
Sync.Map gives us this beautiful, elegant solution to this problem, a single method called load or store. This method is what we call atomic, which just means the whole thing happens as one indivisible step. No other process can jump in and interfere. It is specifically designed to handle this check-then-set pattern safely.
And here's the magic. Load or store basically says, hey, look for this key. If you find it, great, just return it. If you don't find it, store this new value I'm giving you. The crucial part is that this whole operation is atomic, so only one Go routine will ever actually do the store, and all the others will get back that same consistent value. No stampede. It's brilliant. So at this point, our developer Ethan, he is just blown away. He thinks he's found it, the ultimate solution to all his concurrency problems. But this is where he, and honestly, so many other developers, are about to make a huge, huge mistake.
He is ready to do a global find and replace, to just upgrade every single map in the entire project to this new, supposedly superior version. I mean, it seems logical, doesn't it? If it's better for one thing, it must be better for everything. But he could not be more wrong. This right here is the single most important moment in our entire explainer. Because using a specialized tool for a general-purpose job is a classic engineering blunder.
And that brings us to the most crucial lesson of all. This isn't just about knowing what a tool does. It's about knowing when, and maybe more importantly, when not to use it. This is the difference between being a coder and being an architect.
So let me be perfectly clear. Sync.Map is not a magic upgrade. In fact, for most of your common use cases, a standard map protected by a good old RW mutex is actually significantly faster and, thanks to type safety, a whole lot safer too.
So when should you reach for sync.Map? It's really optimized for two very specific scenarios. First, for write once, read many data, like a cache that hardly ever changes. And second, when lots of Go routines are writing, but, and this is key, they're all working on totally separate keys, so they're not stepping on each other's toes.
For literally everything else, any situation where keys are getting updated or overwritten a lot, the simple, old-fashioned map with a mutex wins. Hands down. The internal magic in sync.Map actually breaks down under those conditions, and it becomes drastically slower.
And this really gets to the core lesson here. Look, it's easy to learn what a tool does. The real skill, the thing that marks a true architect, is understanding its trade-offs and knowing its limits.
So I'll leave you with this question to chew on. Every single field has its own version of a sync.Map, right? A powerful, specialized tool that is so often misunderstood and misused. What's the one in your world?